Hi, everyone. I'm Karen Ng, class of 2002, Core 6, and I'm the president of the MIT Club of Hong Kong. On behalf of our club and the Club of Beijing, it is my honor to welcome you to this webinar featuring Professor David Autor tonight, or this morning, in Cambridge. Well, Professor Alton needs no introduction, but I will go through his bio quickly. Um, he is the Daniel and Gail Rubenfield Professor in the MIT Department of Economics, co-director of the NBIER Labor Studies Program and the MIT Shaping the Future of Work initiative. His scholarship explores the labor market impacts of technological change and globalization on job polarization, skill demands, earning levels, and inequality and electoral outcomes. Professor Autor has received numerous awards for both his scholarship, the National Science Foundation Career Award, and Alfred P. Sloan Foundation Fellowship, the Sherwin-Rosen Prize for Outstanding Contributions in the Field of Labor Economics, the Andrew Carnegie Fellowship in 2019, the Society for Progress Medal in 2021, and for his teaching, including the MIT MacVicar Faculty Fellowship. In 2020, Professor Autor also received the Heinz 25th Special Recognition Award from the Heinz Family Foundation for his work in transforming our understanding of how globalization and technological change are impacting jobs and earning prospects for American workers. In 2023, Professor also was selected as one of 2 researchers across all scientific fields, a NOMES Distinguished Scientist. Um, the Economist magazine labeled Professor Autor in 2019 as the academic voice of the American worker. And later that same year, and with equal justification, he was christened Twerpy MIT Economist by John Oliver of Last Week Tonight in a segment on automation and employment. We were very honored to have Professor Autor speak to us 3 years ago to the MIT Club, actually also November 2021, about where new work is coming from. But with the changes with the developments of AI and everything that's going on around the world, we're very glad that we can welcome the professor again to speak to us on where the future of work is going. So with that, Professor Autor, thank you.
Thank you very much. Thank you, Karen, for that very generous introduction. It's a pleasure to be here, and I believe at least one of my students, former students, Anton So, is out in the audience. So shout out to Anton, and always exciting to address MIT alums. I've been an MIT faculty member actually since 1999. I consider myself very privileged to be part of the institute. So let me share my slides. Here we go. Okay, with luck, you can see that. You'll let me know if otherwise. So I'm going to speak about expertise, artificial intelligence, and the work of the future. So start off by considering these 2 jobs, air traffic controller, crossing guard. What's the difference between these 2 jobs? They're actually basically the same job. The job is to prevent collisions between aircraft and ground vehicles or aircraft to one another, but also between children and passenger cars. And yet, although they're doing basically the same work, a crossing guard makes less than 1/4 of what an air traffic controller does. Why is that? It's not because that work, being a crossing guard, isn't extremely valuable. If we had to spend $130,000 in the United States to prevent our children from being hit by motor vehicles on the way to school, we would certainly spend that money. The difference is expertise. To become a crossing guard in the United States requires no training or certification in almost any US state. Any able-bodied adult can do this job. To become an air traffic controller, on the other hand, requires years of air traffic control college, then hundreds to thousands of hours of apprenticeship to master that expertise. So the difference between them is expertise. One way to say that is if we suddenly needed more crossing guards, we could get air traffic controllers to do their jobs. If we suddenly needed more air traffic controllers, we could not get crossing guards to do that work. So let me define terms. I said expertise. What is expertise? Expertise, I argue, is what makes labor valuable in industrialized countries. What it means is domain-specific knowledge or competency to accomplish some particular goal. It could be to code an app, to bake a loaf of bread, to remodel a kitchen, to care for a patient, to land an aircraft. Not all expertise is economically valuable. You might be expert in stamp collecting. It's hard to make a living doing that. You need two things for expertise to have market value. One is the goal it enables must itself have market value. So it's got to be, data science, not card tricks. The other is the expertise must be scarce because if everyone is expert, no one is expert. Expertise by definition means something that's worth doing that not everyone knows how to do. And that also highlights, and sort of a theme of my talk, is that what constitutes expertise is a moving target. It changes over time as a function of what society is doing, what technologies are available, and what people have mastered and learned. Why does it matter? It matters because non-expert work is paid poorly. Think of the jobs of waiter, cleaner, janitor, security guard, school bus driver, daycare teacher, crossing guard. Some of these are life and death activities, and yet they pay poorly in industrialized countries because the set of workers who can do them is not scarce. They're not expert. Many people can do that work without training or certification, and that tends to mean they will be paid low wages because the labor is abundant. So expertise is the theme of my talk, and I want to talk about expertise in three different eras. One in the Industrial Revolution, two in the computer era, and three in the artificial intelligence era, in which we have recently entered. So let me just, to set the stage, talk about the Industrial Revolution. But before I do, I want to make the following point. You might think that in the richest countries in the world, whether they're in Asia or in North America and Europe, where we have so much capital, so much technology, so much infrastructure, that labor would play a relatively small part in economic activity. But the opposite is true. In North America, 6 out of every $10 goes to labor before it goes into the rest of the economy. It's paid to workers. The world average is 54%. In some parts of Asia, it's about 50%. In North Africa, it's as low as 40%. So what's amazing about this is after 200 years of automation and new technologies that have moved people out of agriculture, moved people out of physically demanding labor, moved people out of repetitive work, the value of labor has risen, not fallen. And when I say risen, I don't just mean we're paid more per hour. I mean that the share of all output paid to workers has risen. And that's a remarkable accomplishment. That value, essentially, it means that expertise has become more valuable over time. That's something that we should not take for granted, something we should think of as an amazing achievement, but also something we should worry about the possibility that we could lose that achievement. So let me now talk about expertise across time. So the Industrial Revolution was a big idea. It was not just a technology. It was the idea of taking artisanal work, the slow craft work of making fabrics, making metal objects, putting horseshoes on horses, making boots, done by skilled artisans, one object at a time, and breaking it down into a series of small repetitive steps that could be accomplished by machines, managers, and really untypically low-skilled, non-expert workers. This transition into the Industrial Revolution began in the late 18th century, and the first 6 decades of it were actually not a good period for workers. The evidence is that the real living standards of the British working class did not rise for the first 60 years of the Industrial Revolution. Why? Because the labor that was required to work in the early factories was unskilled and inexpert. Often the work was done by children, by indentured workers, by unmarried women. They worked in dangerous, polluted conditions, and they were disposable, interchangeable. That began to change in the 1860s or so, when the work became more sophisticated, the machines became more complex, the inputs became more valuable, the expectations of quality changed, and eventually you needed workers who knew something. They knew how to follow rules, how to operate tools, and often they needed literacy and numeracy. So these two figures, one from a Ford production plant, one from the typing pool of the International Harvester Company, illustrate what I call the era of mass expertise, where these workers were not artisans, right? They couldn't make a car from back to front or run their own business necessarily based on what they had learned, but they did use formal knowledge and literacy and numeracy to accomplish relatively expert tasks. And because this was such a productive way to use labor, this combination of repetitive work, mass expertise, machinery, that it really led to the rise of living standards, along with many other changes, over the course of a kind of 100 years, from 1860 to 1980 or 1960, throughout the developing world. So the rise of mass production and mass expertise along with it not only increased productivity, but increased the value of labor. And it was, in many ways, a remarkably successful economic period in human history. That begins to change in the 1970s, the 1980s, with the computer revolution. So let me remind you what is distinct about a computer relative to other machines that historically people have used. So to illustrate that point, I want to show you the Jacquard loom, which is really what many would consider the first industrial computer. So the Jacquard loom is a loom, but unlike prior looms, it actually follows a program. What you're looking at, these brass plates here, are punch cards with instructions to loom about what arms to lift, what pattern to weave. These are not paint by numbers. This is not a picture of the pattern the loom is supposed to weave. It is a set of instructions. The Jacquard loom was the first commercial symbolic processor, meaning it accessed, analyzed, and acted upon information. And so those punch cards could have been made of, they could have been made of brass, they could have been made of wood, they could have been made of paper. The key thing was it had symbolic code. This was such a powerful idea, in fact, that Herman Holrith took inspiration, invented the paper punch card that was used to read the 1890 U.S. Census of Populations, the first machine-read census of populations. He joined forces with Thomas Watson to form a company called IBM. So this is really the genesis of the modern computer era, really starts with this physical machine. And what was distinctive about the symbolic processing, it allowed machines to also to follow rules and operate tools, a lot like those workers using mass expertise that I mentioned a minute ago. So this actually enabled machines to do a whole set of tasks that previously, because they required cognition and thinking, were exclusively in the mind's domain. But there's an important difference between computers and labor in this era, which is that there was at least a trillion-fold decline in the cost of computing over the last 75 years. So what do I mean by trillion-fold decline? So William Nordhaus, a Nobel Prize-winning economist at Yale, tried to estimate the cost of carrying out 1 million mathematical calculations between 1850 and 2007. And from around 1850 to 1950, there's actually very little change in that cost. You'd say, why? Aren't people getting more literate and numerate? And the answer is yes, but the cost of labor is rising. And in fact, even in the early 20th century, they were adding machines and mechanical devices to speed up computation. But there's really very little change. And then with the invention of first the vacuum tube, then the transistor, and then the integrated circuit, and then the microprocessor, this cost starts to fall year on year at an extraordinary rate. So if it cost $1 trillion in 1950 to do 1 million calculations, it would cost $1 by 2007. So that's a remarkable price change, and it has important implications for workers because, of course, computerization could carry out many of those rules-based tasks that were being executed by workers on assembly lines and in offices. And so it potentially replaced production workers, office workers, clerical and administrative workers. And you can see that in this figure, which shows you the change of employment in major occupation categories in the US over a 45-year period. These occupations are ranked from low to high paid. So on the left-hand side, you have personal services, cleaning and protective services, laborers. These are those inexpert, hands-on service occupations, socially valuable, poorly paid because the expertise is not scarce. In the middle, you have a lot of those mass expertise jobs, production, operative, clerical, administrative support. And then at the top of the figure, you have technical, professional, and managerial jobs. These are highly educated jobs that require judgment, expertise, creativity. And so computerization contributes to this barbell pattern with this sort of falling weight in the middle of the bar and growing poundage on either side. And this coincided with an era of rising inequality across much of the industrialized world, where the real wages of highly educated workers rose and the real wages of non-college workers fell, especially among men. And partly this reflects the displacement of those mass production workers into those generic services. Services, again, socially valuable, poorly paid. Now you might be asking, well, why this barbell? Why the middle but not the edges? Oh, and the answer to that question comes down to what some call a Polanyi's paradox, after the philosopher Michael Polanyi, who made the following observation: we know more than we can tell. Many of the things that we do on a regular basis, we don't actually formally understand how we do them. So we know the rules for adding and subtracting numbers, but we don't know the procedure, the program for coming up with a funny joke or making a persuasive argument or developing a new hypothesis. We also don't know the rules and procedures, by the way, for reaching into your purse and finding your wallet, or actually folding a shirt, or buttering a piece of toast. These are actually incredibly challenging problems in robotics. So how do we do them, even though we don't know how to do them? We learn them tacitly. We learn them through experience. When you learned how to ride a bicycle, you didn't take a class in gyroscopic physics. Your parents probably put you on a bike on a gentle hill and gave you a push and said, well, good luck. I hope you figure that out. And most of us did. And that's because much of human learning, in fact, is done tacitly. And that has an important implication for technology and automation, which is that historically, before AI, we couldn't computerize tasks that we didn't explicitly understand, that we didn't know the rules, because we couldn't write the program. We couldn't produce those punch cards that told a computer how to come up with a new idea. Um, and so that was really a key limitation on computing until recently. And those of you who have done computer programming, which I think many of you do, you know what I'm talking about, right? When you first started to use a program, a computer, you were first impressed, and then you thought, why is this thing so stupid? It never does anything other than when I tell it. Can it see what I meant? Doesn't it see a shortcut? And the answer is, of course not. It doesn't. It just follows instructions. So now we are in a different era, of course. We have machines that can do tasks that look nothing like those following the rules, look nothing like the Jacquard loom, right? They can learn autonomously from unstructured information. They can do tasks that you would think of as creative if they were done by people, like making these illustrations. They can discover and invent on their own. Just to highlight an amazing example of that, you may have heard of the program called AlphaFold. So in structural biology, a key challenge is to figure out the folding structure for proteins. You often know the sequence of amino acids that makes up a protein, but that doesn't tell you its exact shape. And this is what a protein might look like. It looks like a party streamer. It's incredibly intricate. Why do you need to know the folding structure? Well, that actually determines the way it interacts with the body and with other materials. If you're making a medicine, you need to, a medication, you need to understand not just what is the sequence of amino acids, but actually what is the physical structure of the protein. This was such a hard problem that a biologist named John Molt had been running a contest since 1994 called the Critical Assessment of Protein Structure Prediction Competition, or CASP. What it was every year a set of teams would enter. Molt would give them the amino acid sequence of a set of proteins for which they did not know the folding structure. And then they would have a few days to make their best predictions about how those proteins folded. And then he would grade them and announce the winner. In 2018, DeepMind, now a company owned by Google, but not at that time, entered a piece of software into the competition called AlphaFold. And in Science Magazine in December 2020 wrote, "The game has changed. AI triumphs at protein folding. This piece of software just cleaned up." Science said, "Artificial intelligence has solved one of biology's grand challenges." John Molt, the founder, said, "This is a 50-year-old problem. I never thought I'd see this in my lifetime." And in fact, last month, the Nobel Prize in Chemistry was awarded to Demis Hassabis and John Jumper of DeepMind for this piece of software. Okay, so that's what AI can do. And you can see how different that is because it is solving a problem to which we don't know the answer. And in fact, we don't even quite know how it's solving it. AI is not very transparent. It's not very legible, as the term goes. So now let me get back to labor economics. That's where my talk is focused and where my work is focused. And because I think the labor market is so central, how should we think about this new capability in relation to labor and in terms of what workers do and how they will use machines? So let me stipulate first that AI is a tool like a calculator or a chainsaw. We should think of it as a tool. And most tools are not frightening to us. They are not our enemies or our competitors. They're our friends, right? So if you're a doctor, you wouldn't want to do your work without a stethoscope. If you're a roofer, you wouldn't want to be without your pneumatic hammer to speed up your work. If you are a air traffic controller and you don't have a two-way radio, a GPS, and a radar, you are just a person standing in the field staring at the sky, right? You cannot do your work. So in many ways, tools embody or enable us to use our expertise by shortening the distance between intention and result. And so much of our expertise, in fact, is bound up in our knowledge of how to use those tools. And so a good scenario for AI is it could enable people to extend their expertise more broadly, to take the same knowledge and judgment and do a greater variety or more difficult or previously infeasible set of tasks that will be valuable to them, valuable to society, and therefore well paid. But not all tools are the friends of expertise. Since 1894, London taxi drivers have had to spend about 3 years memorizing what's called the knowledge, which is an exhaustive memorization of all the routes and highways and underpasses of London. It's a hugely expert task. It is such an amazing feat of memorization that brain scans show changes in the myelination patterns of the hippocampus as a consequence of this memorization. But of course, that valuable expertise was made kind of economically irrelevant by Waze, Google Maps, Apple Maps, because not only do those ride-based hailing apps know all the streets and highways and byways and underpasses of London, but they also know how much traffic is on those routes at any given moment, which is something you can't memorize. And so when ride-based hailing was introduced and when GPS was introduced, all of a sudden, London taxi drivers had a lot more competition. In fact, their wages began to fall until they unionized. So it's quite possible for AI to commodify or strand expertise. Many technologies have done this historically, so it wouldn't be something new under the sun. But of course, AI puts a different set of forms of expertise at risk. So let me go further in saying, well, how can we think about this concretely? So let's first remind ourselves that AI is already woven into daily life. You were using AI long before you ever heard of ChatGPT, right? So if your smartwatch asks you if you've taken a fall, or your car tries to steer you back into lane on the highway, or your writing application offers to assist you with your writing task, these are all instances of AI reading the environment, picking up cues, and then trying to predict what you want and help you take the next step, whether that is calling for emergency help, steering back into lane on the highway, or finishing your writing assignment. And in fact, a lot of AI applications at present and at forward will be machines that pay attention to what we're doing and try to help us accomplish the thing we're setting out to accomplish. So let me talk about what are the upsides and downsides of that. I want to talk about both the promise and the peril. Let me begin with the peril, and I think this is going to illustrate some examples, not just because they're sensational, but really because I think they exemplify some of the big challenges up ahead. So in June 2009, Air France Flight 447, with 228 people aboard, 12 crew and 216 passengers, left Rio de Janeiro on a routine flight to Paris. Shortly after it got out over the Atlantic, the pitot tubes, which are just the speed sensors, iced over at about 35,000 feet. This is not unusual. But it is a problem for the autopilot. The autopilot can't operate if it can't sense the velocity of the aircraft. So the autopilot, recognizing that it had lost the ability to sense velocity, partially disengaged, as it's supposed to do, and it notified the crew that it was doing so. When that happened, the plane rolled a bit. In the confusion that followed, the crew stalled the aircraft. What does it mean to stall an aircraft? So the principle on which an airplane wing creates lift is called the Bernoulli effect. The air passes over the wing on the bottom and the top, but it's a longer way around the top than the bottom because of the curvature of the wing. And that creates a low pressure zone at the top that gives the airplane lift. If the angle of attack of the wing, that means the angle of the wing relative to the airflow becomes too steep, you lose that laminar flow, you lose the Bernoulli effect, and the plane loses lift. So you can stall at any velocity if the angle of attack is too steep. And that's what occurred. During the 3.5 minutes between when the autopilot turned itself off, or not even all the way off, but part of the way off, and the plane collided with the water, the crew did not understand that the plane was stalling. The cockpit voice recorders from this crash have been recovered, and you actually hear the autopilot saying, "Stall, stall, stall." And you hear the crew saying, "What is happening? What is happening? I do not understand what is happening." Only in the final seconds does it appear that the captain realized that the plane had in fact stalled, but at that point, it was too late to recover. So the accident report for this horrific crash, which killed almost 230 people, was simply this: that the crew lacked experience on the characteristics of high altitude manual flying. And so what this is a negative interaction between machine capability and human expertise. In particular, human expertise was degraded by losing contact with the knowledge to operate the plane. And this is a risk. Now you might say, well, how often does that occur? Isn't that an extreme example? Of course, the answer is it is an extreme example, but it occurs actually surprisingly often. So let me give you a recent example from research by my colleagues Nikhil Agarwal and Tobias Sauls, among others. And they studied an AI support tool called CheckSpert, Chest X-ray Expert. And what it does is it reads chest X-rays and reports to radiologists what it sees. So for example, in this figure, it sees an edema in this red square. It says it's very likely. It thinks pneumonia is quite likely over here. And then other things are less likely or more likely. And this, as you can well imagine, is a great application for AI because there's no hard and fast rules for reading X-rays. You see something, it looks like something that may be problematic or may not, and you develop judgment for picking those cases out. And this machine is pretty good. So using only clinical data, not other contextual information, it does as well as about 65% of radiologists using the same data. So really as good as 2/3 of radiologists. So you might think that the combination of CheckSpert and radiologists would be even better than either one of them on their own. But in fact, it's worse. Radiologists do systematically worse using CheckSpert than they do working independently. Why is that? Well, it turns out the problem is what my colleagues call correlated uncertainty. The doctor and CheckSpert are looking at the same data. They're looking at the same scan. So obviously their views are going to be correlated. And in general, when the software is uncertain of what it sees, the doctor will be pretty uncertain of what she or he sees. When the software is very confident of what it sees, doctors will often also be pretty confident. So what happens when they disagree? Well, what tends to happen is when they're both uncertain, the doctor will defer to the software. When they're both confident and yet they disagree, the doctor will override the software. Well, it turns out that neither of those is the right instinct. When there's a lot of uncertainty, people are actually much better out of sample. They're much better with the edge cases. And the reason is because they're not just using probabilities, they're reasoning about how the world actually works, how lungs actually work, et cetera. So they should probably be overriding the software. Conversely, in the case where they're both confident and they disagree, doesn't mean the software is always right and the doctor is always wrong, but it does mean the doctors say, look, this thing has seen more scans than I will see in 10 lifetimes. So if it's confident and I'm confident we disagree, I should at least think about why it thinks something different. So this is a remarkable result, and we only know it because my colleagues got a big grant from the Sloan Foundation to run an experiment where doctors thought they were reading new X-rays, but in fact they were reading old X-rays where the answer was largely known, and so they could check their answers against ground truth. What this example illustrates is not that this is a bad piece of software or that those are bad doctors, but that this is not an effective way to use AI, or at least not an effective way to train people to use AI, because those doctors had no way of knowing whether they were making good decisions or bad decisions. You see a patient and you say, looks fine, go home, or here, let me refer you to someone else for additional evaluation. You'll never know if you made a good answer, a good call or not. Maybe for years down the road you will, but it'd be hard to attribute it. And so judgment was needed. Judgment was needed, and doctors did not have the judgment, just like those pilots didn't have the judgment to fly the plane when they had another instrument that was in between them and the work. So there's a way to do this right, and there's a way to do it wrong. And more often than not, I would say, it is being done wrong. So now let me talk about the upside potential, about augmenting human expertise, about extending its reach or its relevance. So let me start with another study by actually students of ours, Ked Noy and Whitney Zhang. And they did an early study using ChatGPT 3.5. It was actually published in Science magazine. In Science in 2023. And what they did is they went on Prolific. Prolific is like a kind of an Amazon Mechanical Turk for college graduates, a platform where you hire people to do small tasks. And they chose people who were college graduates who did some writing for a living, and they gave them two tasks. One was to write some advertising copy. The other was to do a very, very brief marketing analysis. And these tasks took about half an hour on the first try. And then after the first task, randomly, they chose half the group and said here individually and said, hey, here's a tool called ChatGPT 3.5. You could use it in addition to Google and your writing software to help you do the next assignment. If you want, here's a little bit of training. About 80% of people took that up. So what you see, the green line is people who are given ChatGPT or offered it. The black line is those who are not. The time spent between on the second task for the control group took about 28 minutes. For the treatment group, it took about 18 minutes. So about a 40% time savings. Okay, that's good. Save some time. The next result is it also improved the quality of the work. So they hired other college graduates, double blind, to evaluate the output on brevity, precision, creativity. And the group that used ChatGPT got about a half a standard deviation better. So that's probably, they did increase them relative to others by about probably 15% in the rankings. But here is the most remarkable result. So if you look at people's performance on the first task, which is on the horizontal axis, and the second task, which is on the vertical axis, here's the group that didn't use ChatGPT, and this slope is about 0.5. So what it says is if you did well the first time, you probably did pretty well the second time, and vice versa. If you didn't do that well the first time, you probably didn't do that well the second time. Here's the group that used ChatGPT, and you see this kind of leveling up. The least effective writers using regular tools were about as good as the median writer using ChatGPT. And in fact, this slope is shallower all up and down the line. Now, this group was not better than the best writers, but it compressed the differences. And that is an unusual result. Some people call this leveling up. And we've actually seen this in several places, not just in writing, but for example, in customer support tasks. People using AI converge towards expert performance more rapidly. They don't start off well. They don't start off expert, but they learn more quickly to how to provide the right answers. People who are writing software using GitHub Copilot and other tools like that, novice software developers seem to benefit more and improve faster when they're using those tools. So we have examples that look like this. And it's exciting, and I want to emphasize it's too early to draw general conclusions. But let me give you another example that I think is even more amazing or equally amazing and quite nuanced and also brand new. This is actually by one of our current PhD students, Aidan Toner Rogers, and he looks at the use of generative AI in material science. So material science is the branch of science that basically develops new materials that have specific properties. You might want them to be have high stickiness, to be glues, or to be heat tolerant, or to be very flexible, etc. And so this is critical to the design of vehicles and aircraft and semiconductors and optical equipment and sort of everything, probably to food, as far as I know. And it's become generative AI material science is a really big deal. So just in the last few years, more than almost 1,000 PhD syllabi in material sciences mention generative AI. And if you look at publications, there's a couple thousand. How does this actually work? The way it works is what is called inverse material design. You start with a set of target features. This is fed into the neural network. It's represented graphically, and then it predicts a structure of a material that would have those features. This is done through what's called graph diffusion. So you start with a known compound, you add noise, you get a random compound, and then you denoise it and come back with a different compound. This is actually like image generation. So stable diffusion refers to this process. So let's talk about what happened here. I want to give you two sets of results, one having to do with productivity and the other having to do with work. So on the productivity side, this company actually ran a big experiment. They rolled out this technology in waves to different teams. So what you see is the rate of production of new materials rose by about 40%. The rate of patent filing within a year rose by about 30%, and the rate of producing new product prototypes rose by about 20%. So that's remarkable. In fact, the products that were produced, not only were they coming out faster, but they were closer to targeted specifications, and moreover, judged by a certain set of standards, a little bit elaborate to explain, they were more creative, they were more novel. So this was working really well. Now let's talk about how this worked for scientists. So what you see here is what Aidan calls the discovery curve. The discovery curve is you have a bunch of ideas. You'll say you have 10, 20 ideas that you want to experiment on. And if you're a rational experimenter, you'll start with your most promising ideas and work your way down the curve. And that's what happens. Without AI, people start their first experiment has about a 90% success rate, and then their 10th experiment has about a 10% success rate. When people start using AI, this first success rate actually falls, although there's a longer tail of successful experiments. So it's clear that people have a harder time of judging what's going to work. If you look at the people who ex ante are least productive, they actually start doing terribly once they use the AI. Their choices are only as good as random. When you look at the people who have the best judgment prior to use of AI, the most productive, you see that their ability to assess the best experiment also falls from basically 100% to 80%, but you get this long tail of good discoveries. What this means is the top quartile of scientists really benefited from using this tool, but the bottom quartile didn't have the judgment to use it well, and they really didn't succeed with it. Part of the reason is because the job changes dramatically. It changes from people used to spend 40% of their time generating new ideas, and then a quarter of their time judging them, and then another 35% experimenting on them. Once generative AI is in use, it does a lot of the idea generation, but scientists spend more time trying to judge and discern which are the viable ideas and which are not, and then finally they experiment. And so it really increased the payoff to judgment. And so this again emphasizes the point that with the radiologists, with the pilots, and even with the writers, that human judgment is a critical ingredient into using this tool well. All right, let me just skip the slide. So just to summarize, we've seen this kind of leveling up in several experiments in customer support, professional writing, software development, but there's going to be all kinds of different effects. Some jobs will be directly displaced. We should not pretend that's not true. They will. Some cases, AI will create superstars, people who can do the work of many with only one. We'll see that in things like finance, though we won't see that in medicine where there's so much hands-on work. In some cases, it'll just make expertise less valuable, even though it won't eliminate it. In the interest of time, I'm going to shorten this a little bit, but an example I would go into at greater length is the job of nurse practitioners who are expert medical professionals who have 5 years fewer education than medical doctors who now use many tools. They use electronic medical records, diagnostic software, prescription drug interaction software to enhance their capabilities and allow them to provide more services and accomplish more tasks. And I think the future of using these tools well means complementing expert judgment, like those nurse practitioners, for example, to extend the range of things that people can do. That is the good scenario. Now, let me end by talking about the end of work. You may be thinking, I keep talking about, what type of jobs people will do, and you may be wondering, will they have any jobs at all? If you have that concern, you're in distinguished company. I wouldn't say you're in good company, but you're in distinguished company. Here's Elon Musk saying in 2023, there'll come a point where no job is needed. Here's Geoffrey Hinton, who actually won the Nobel Prize also in October for his work on artificial intelligence. And he said, get a job as a plumber. So what they believe is that we have a future where either there'll be no work or everyone will be working as a plumber. This doesn't sound like an interesting economy to me, and it doesn't sound like a likely one either. I'll tell you 2 reasons why I think this is incorrect. First, let me start with a very concrete reason. We're not running out of jobs. We are running out of workers. So if you look across the in Western world or throughout Asia, what you see is a huge decline in the number of working age adults. So between 2020 and 2060, Korea expects to see a 40% drop in the number of working age adults. China expects to see a 30% drop. And this is the United States is barely holding its own, and if it restricts immigration further, this will become negative. Why is that a problem? I say, well, fewer people need fewer jobs. But the problem is when you start running out of young people, you don't run out of old people. You have a lot of people to care for, and those people have earned a retirement, and it requires a lot of productivity and workers to support them. So we are in no sense running out of work. In fact, labor markets are tight throughout the industrialized world. Now, of course, we all recognize that there are many people throughout the world who would be happy to come to these rich countries and work. So there is not a global labor shortage. But unless immigration policies change greatly throughout the world, which I wish they would, but I don't expect they will, this problem will be with us. But let me point to a more fundamental fact is when many people think about new technologies, they think about what they automate, how they allow us to do the same old stuff better, cheaper, faster. But in reality, most innovations are not fundamentally about automation. And certainly the most important innovations are not about automation. When humans learned how to fly using machines, that didn't automate the way they used to fly. They just couldn't fly before they had flying machines. When the scanning electron microscope was invented, that didn't automate the way we used to look at subatomic particles. We just couldn't see them. If you went back to ancient Greece and automated all the work they did, you would not have modern Hong Kong. You would have ancient Greece without horses. It wouldn't have flight. It wouldn't have telecommunications. It wouldn't have penicillin. Technologies are transformative, not simply because they make the old stuff better, cheaper, faster, but because they create new capabilities, enable new capabilities that we previously lacked. And AI will be the same. So instead of asking, what will AI do to us? We should be asking, what do we want it to do for us? How do we want to use it? We have a lot of choices. I'll give you a concrete example. In the early 1940s, humanity mastered controlled nuclear fission. There are two good ways to use it, or two well-known ways. One killer app is to make nuclear weapons, and your neighbor North Korea has many, many of them. Another is to make nuclear power plants, and your neighbor Japan has many of those. In fact, North Korea has no nuclear power plants and an impressive arsenal of thermonuclear warheads. Japan, the only country against which a offensive nuclear weapon has ever been used, has no nuclear weapons and multiple dozens of power plants. So that's not a function of the technology. That's a choice of what to prioritize. And this is true with AI as well. We can use it for surveillance. We can use it for censorship. We can use it for all kinds of bad uses. We can also use it to assist with elder care, to provide real-time information to workers doing diagnosis, maintenance, repair. We can use it to make learning more immersive, more engaging, less expensive, more accessible. These are all possibilities. They require investment. They require investment in the technology and capabilities. So when we say, what do we want to use AI for? We should be asking, how do we use AI to empower and extend expertise? If we want to do that, how do we make it happen? This is not an easy problem. It's not a matter of saying that's what we'd like. We need R&D. We actually need to invest to discover how to do that well. And this is a collective choice shaped by industry, by government, by universities, by trade unions, all of them that participate in setting these priorities. So let me end on a positive note. So my washing machine has an application, a smart app, and it actually my washing machine actually has more processing power than the Apollo guidance computer that was used to land the first people on the moon in 1966. And this allows me to start my washing machine from anywhere in the world. And of course, this is a useless application of technology. I don't need to start my washing machine remotely. My clothes are at home. And my washing machine is never going to the moon. And so the difference between these two technologies is not how much processing power they have, but what a reach of imagination they were. The Apollo's guidance computer was a moonshot. The Whirlpool washing machine is a gimmick. And so when thinking about how to use AI well, we should be thinking beyond simply replicating human capabilities, beyond making things better, cheaper, faster. we should be looking for moonshots. And by finding those moonshots, we'll find a better way to use these tools and take advantage of the opportunity that we have created for ourselves. Okay, let me stop there. Okay, let's see. All right, so I think I'm gonna take your questions. I see 2 questions already, so let me try to ask them. The first question is it not the case that expertise exists because there has not been AI up to this point? No, I don't think that's a great question, a very funny question. But no, expertise exists because we create more tools and opportunities that require knowledge. So in fact, most technologies create new demand for expertise because they create new tools and new understanding, right? So, we didn't have pediatric oncologists 50 years ago. We have them now, and that's a function of accumulation of knowledge and improvement of tools. And so I do not think AI is going to eliminate all expertise. I think it's going to require expertise. Some expertise will be eliminated, but that is I don't think that's the end of it. Although I understand the question. Another person says, Eric Chang, a team of 10 programmers may be replaced by 3 senior programmers in AI. So jobs may not disappear, but some workers will still be impacted. What is your advice? Okay, good. So that's absolutely right. I completely agree with that point. And I want to emphasize that although I am optimistic about the potential for how we can use AI well, I simultaneously recognize that there will be real costs. And I think most people are either extremely pessimistic or extremely optimistic. And I actually think you ought to be both simultaneously, recognizing that there will be real social costs as well as social benefits. So in terms of what do we do about that? Well, what we ought to do is, of course, this is a long-term problem, a problem we've always had about long-term unemployment. And the way that we're most effective at that, one, is by providing social supports, by providing retraining, by providing active labor market programs that help people redeploy. But of course, it's psychically costly, it's financially costly, and so that's not a simple solution. It's really problematic for people, and a lot of adjustment is generational. One hope, this is not, again, a solution, is that we will also use these tools to create better education programs, right? So adults don't like going back to classrooms. They learn immersively, they learn tacitly, as I was speaking of earlier. Most of us do. And so one potential for AI is actually to use virtual reality to create things that are more like flight simulators or medical simulators to allow people to acquire skills through practice rather than just through blackboards and tests. Okay, let's see. There are so many good questions here. Wow. How should universities educate students to help them prepare for the age of AI is a question asked by Eric Chang. Super important question. Not one that I know the answer to at this point. But again, I think thinking of this as a tool, we should be asking, well, how do we use this tool well, and when would we be using it badly? I think the real, danger here is that you need foundational judgment to make good decisions. And so although we don't ask children anymore to memorize, times tables necessarily, we do expect them to know addition, subtraction, multiplication, and division. And if they didn't know that, it would be dangerous for them to do higher level mathematics because they wouldn't have the common sense to see if they were making a mistake. And so the danger with AI is if we actually, writing is hard. If people kind of lose the ability to write or communicate clearly without aid from machines, that's going to be a problem. So in all cases, we should be asking, how do we use this tool to leverage what we do without making us like those pilots who were lost without the autopilot? So I don't think there's a simple answer. And I think it's going to take a great deal of experimentation to figure this out. And a lot of that's going on right now. Okay, a related question by Alberto Mol. How would you deal with the fact that junior symbolic analysts need to be trained by senior people when senior people will no longer need the junior analyst? What happens when the senior analyst retires? Excellent, excellent question. There's actually a former MIT student at the MIT Sloan School named Matt Bean who studied this exact problem in the case of robotic surgery. So robotic surgery is where a doctor uses a robot to do the physical manipulation of the patient, and the doctor watches from a screen, and this can be very precise, less invasive, and less damaging to the patient. It also requires fewer medical assistants around. And so when surgeons started using robotic surgery, they started doing better work, and it sort of cut out the training ladder for people who were learning. And in fact, in Matt's book, The Skill Code, he talks about basically junior medical residents who would find ways to operate at night, not on patients, but on other things, just to practice with this machine. So I think we actually need to be extremely cognizant of how we continue to enable people to build judgment uh, as we use these new tools, because it really is a danger that we will cut out the learning process, and all of a sudden we won't have senior people who can who rise up from the junior level who are able to do that work. So, for example, the example I gave of those material scientists, it was the experienced scientists with judgment who did well in this setting, and others were much less productive. But they got to be senior and have good judgment because they had a lot of practice. Karen, did you want to speak to? Am I at time?
No, you still have 10 minutes.
Oh, okay, great, fabulous. Um, let's see.
And the
uh,
question is, how
yep.
do you want AI to do for us? You mentioned about we train the AI. How do you want AI to do for us? Create PA, TA, waitress, or any shortage of labor force? This is a question by Shirley Xu.
Sorry, can you ask the question again? I didn't quite hear it.
Sorry, by Shirley. How do you want AI do for us? Create PA, TA, waitress, or any shortage of labor force?
Well, so I don't want AI. I want us to decide what we want to do with AI. What are the most pressing problems we could use it for? I think is maybe one way to interpret your question. And I apologize if I'm misinterpreting your question. I mean, so I would say, first of all, we face a large number of problems of humanity that we're going to require really complicated solutions, whether those are climate change, uh, energy production, more efficient agriculture, getting medicine and healthcare to much of the world that doesn't have adequate access, or improving education for much of humanity. And AI is going to be helpful both for pushing out the frontier of science, accelerating the rate of progress, and of course for scaling those things. That's especially true in medicine. So that's one thing. And then in the domain of work, the best thing that could happen with AI, in my opinion, is that in most countries, only a minority of workers have, post high school education. In the United States, it's 40% of people who have a college degree. I think it's somewhat higher in Hong Kong. I'm not sure. I apologize if I'm incorrect about that. But so over the last 4 decades, those people with high educations have done great. As I showed you in one of those figures, it's just been a great time. We've been on a roll of rising inequality, rising wages. For everybody else, they've increasingly found their expertise devalued and found themselves in those low-paid services that don't require much expertise. A better world would be one in which they had better tools and training that enabled them to do more valuable work. That work could be medical paraprofessional work, it could be software development, it could be skilled repair and construction, it could be design. There's a lot of work to be done, and we have a shortage of highly educated workers, and in many cases, an excess of low educated workers. And if we could find tools that enable them to do more valuable work, that would be good for lowering prices, it would be good for the quality of work, but it would especially be good for employment, and I think therefore good for the middle class in many societies.
Oh. And there's a question says, in terms of impact of equality, will AI decreases the equality because it depends on who has the capital to own and train the AI?
So this is a very important question. So, so there's two forms of inequality that we talk about a lot. One is inequality between workers, like between workers of different education levels. And then the other is equality between ownership of labor and ownership of capital. And ownership of capital, of course, is much, much more concentrated than ownership of labor, because in a society without slavery or labor coercion, we all own only one worker, and that worker is ourselves. And so it is a real concern. I mentioned at the beginning of my talk how in North America, 6 out of $10 goes to labor. That's a monumental accomplishment. If it were the case that labor's share of national income started falling from 60% to 50% to 40% to 30%, that would be a very serious problem, because it would be, just as it was described, would mean that the owners of machines and so on were creating most of the value or own most of the value. And that politically is not viable. If we look at countries where most of the income comes from materials and resources rather than from labor, where it comes from oil or diamonds or rare earth elements, those societies don't work well politically because labor is not an important constituency in the government. And so I worry about that a lot. And that's why I think it's so critical to use AI to complement and extend expertise rather than simply attempting to replace it.
Then if there's another question from one of the users. It says, the difference between highly educated and the others has created the big chasm between Democrats and Republicans in the US. Will AI aggravate or help this situation?
It is the case that throughout the US and Europe, that there is absolutely a growing chasm between the highly educated and others. And the Democratic Party, which used to be the party of blue collar workers, is now really seen as the party of highly educated adults and people who are connected to the global economy. If AI enables the growth of middle-class jobs, if it now enables more people to do valuable, high-paid work without having elite levels of education, whether that, again, if that's in healthcare services, if it's in software, if it's in design, if it's construction, that will help address some of this polarization. Will it do that? I really don't know. I would like it to do that.
Okay, and since we only have 2 minutes left, maybe perhaps this is the last question, and it's a prediction, Professor. What will AI look and feel like 10 years from now?
So, okay, so I'm not a computer scientist. I think AI is advancing remarkably rapidly, but on the other hand, I do not think it's converging towards artificial general intelligence on the path it's on. I think it fundamentally lacks reasoning. It doesn't understand cause and effect. It does not understand the arrow of time. It's mostly probabilistic, although it's getting better and better in that way, and you can go very far with that. So I don't think it's within 10 years we will have artificially intelligent, generally intelligent pieces of hardware, nor do I especially want us to. I do think actually progress in robotics is accelerating very rapidly. Robotics has always been the sort of domain of imagination for cartoons and movies of these robots that do various things. In fact, I mentioned about Polanyi's paradox. Robotics is harder than cognition because working in the world of objects and physics and the general complexity of that environment has always made it an intractable problem. AI is enabling robots to acquire capabilities faster. And so I do think we'll see a lot more robotics around us. It will become much more common, not necessarily to have a domestic robot, but to have a robot that does deliveries, a robot that does cleaning, a robot that lifts things and shelves things, and ideally also robots that can help with assisting elderly. I don't mean autonomously, but in care facilities or even providing exoskeletons to people who have weak bones to enable them to increase their mobility. So I think that is a very big frontier that we will start to see much more of over the next decade.
Great. Thank you, Professor. I think time has come to the end of the hour. And so on behalf of the Club of Hong Kong, on behalf of the Club of Beijing, and on behalf of everyone on the call, thank you so much, Professor Autor.
Thank you very much. Thanks for inviting me. Nice to speak with all of you.